grand round through this newly formed society that is still in its infancy in a structured way. But the roots of this society goes far back. Maybe some of the seniors here can correct me, but I believe the early ideas of forming this society started in 1991. And then I think 92 or 93 was the first meeting of this society that happened in collaboration with the Pakistani neurologist within Pakistan. So Pakistan Society of Neurology was formed in Pakistan, and Pakistan International Neuroscience Society, or PINS, was formed here in North America. This has been a long-standing collaboration since then with many, many leaders from Pakistani neurology and neurosciences who continued the tradition of annual meetings through updates, presentations, and discussions. And then gradually, as they got busier and busier, this continuity got broken for a few years. We are now planning to restart that tradition and inform the gathering and group of all the neurologists, neuroscientists from Pakistan and North America. We are now doing it in a more organized and structured way. We have registered this organization and getting a 501c status for it. We have started a few years ago with an effort of bringing everyone to a platform. We started a WhatsApp group for the neurologists and neuroscientists in North America, and we have more than 200 members in that group right now. And then we recently formed an executive committee through the first elections with an idea to see if this elected executive body can give it a formal structure and organized structure. So I'm part of that executive committee along with my colleague here, Dr. Junaid Kalia, who will be moderating the session today. And in addition to organizing us, there are a few things that we really are looking forward to doing. For the neurologists and neuroscientists in North America. I'm from Pakistan, and one of our key idea is to promote mentoring, help young faculty, junior faculty, residents in training, and other physicians from Pakistani origin get the guidance that they need, get the breadth of scope of things that are possible, realm of possibilities, to be able to become the leaders in their field. Let me recognize other members of the executive committee who I see in the group here. I see Muhammad Taimur Khan, who is actually the force behind putting this together. I see Dr. Adil Memon, and then I see Dr. Tariq Alam here from the executive committee. So this will be first of our series of grand rounds where we'll invite top leaders and entrepreneurs, especially if they are of Pakistani origin, but anyone who can help guide us as a group and our juniors to promote their careers, to do better, to be a leader from various different backgrounds and aspects. And I am pleased that Junaid and Taimur decided to kickstart this process with a true entrepreneur and a career that is not typically many of us think about when we are thinking mostly of clinical careers. And I think that's really, really important to see all the different aspects of possibilities. So I'm really pleased for Junaid and thankful for Junaid and Taimur for doing this. So Junaid, back to you. Thank you.
Hello, everyone. Thank you so much for joining us. I really appreciate what Don has said. And then the key issue over here is to increase the spotlight on our innovators and then provide their guidance to our juniors. So that's the whole idea behind just not your regular run-of-the-mill grand rounds in producing just evidence-based research, but to get into the nitty-gritty of it, that how to improve entrepreneurship, innovation, etc. So this is fantastic because Dr. Khan Siddiqui is one of the innovators, and he's the perfect example for achieving that excellence beyond clinical expertise. And I'm very grateful that he's on our inaugural session today. Dr. Siddiqui is known for what you can see on his background for Hyperfine, but even before that, he has a significant long history in health information, health technology. He has founded few companies, and he was at Microsoft and has a very significant expertise in image analysis, deep learning, and artificial intelligence. So I'm very grateful, Dr. Khan, that you are here. Before we start, I wanted to make sure that we have some house rules. Please make sure that you're muting yourself. We'll be taking questions. And then if you don't mind putting in the chat, and if there's something that requires more than just chat, I will probably unmute you, and then you can definitely ask your question at the end. The way the agenda is set up today is that we will explore the entrepreneur, his journey, his life, what led to him to be this amazing scientist plus entrepreneur. And then we're going to get into the key discovery that he has produced. So this way we get both the knowledge of the process and the end product. Before I get into that, again, Dr. Siddiqui, thank you so much. And I will give it to you to properly, again, reintroduce yourself, because I'm pretty sure I missed a few things, and then take it from here.
Thank you, Junaid, and thank you, Danish. Great to be here. I'm humbled that you guys invited me in your inaugural session, so I don't think I deserve it, but let's, what I'll do is I'll walk through quickly in my journey through a few slides, just go show one example on how we will get to, one example of how innovation drives, right? It's hardly ever one person, it's always a team that makes it happen. And it's always what I call, it's never rarely a eureka moment. It's always small nudges over time that happen across different people that actually lead to innovation that happen. So let me share my screen and I'll walk you guys through some of the journey. So my journey started in Hyderabad in Pakistan, where I think I was 11 years old in 6th grade, where I got exposed to a PD-11. PD-11 is one of the old school computers that was installed at the Atomic Energy Medical Center in Jamshoro for nuclear medicine gamma camera applications. But as typical, this is what, late 70s, early 80s, that the interface that connected the camera to the computer never came. So there was a computer sitting at Atomic Energy not being used for the clinical application. So my first exposure to computer was in the context of healthcare. I learned how to code on that computer because just sit there, do nothing as part of my, that's another long story why even I was there, and learn how to do, obviously the first program I wrote was the game Hangman on this PD-11 computer. And the journey kind of went from there. That kind of gave me exposure to technology, integral part of healthcare. And can you imagine, this is Jamshoro, Pakistan, where I'm getting exposed to technology in healthcare for the first time in 6th grade as an 11-year-old. So I always seen healthcare as very technology focused. I ended up going to Aachen for my med school. And again, same thing. By this time, I had already built software for enterprise. I had a software company that was doing exam management system that I acquired just before I went to Aachen. And Aachen, I got sucked into literally my second week there into some kind of data analytics projects from faculty, because can you imagine 1990, a med student who knows how to code was a pretty rare occasion in Pakistan, right? So much so that when I left, my final year thesis was on data mining. So did one of the first mainframe data mining projects in Aachen to show that you can actually do total quality improvement projects on financial outcomes and nosocomial infections purely using data from mainframe. And these mainframe used to be an old Meditech system that required punch cards to program this. So it was that kind of that old stuff. And then the database that Meditech system used was called MUMPS. It was built at MGH by two informatics physicians. I didn't know who they were. So, but as learning the database, how to do this stuff, I would email them because their contact information was available in the manual, and they would respond back to me. And what I'd learned later on, that these were the gods of informatics in the US. So it was Octo Barnett and Bob Greenis. Bob Greenis ended up being chair of biomedical imaging at Harvard University, and Octo was head of informatics at Columbia. I didn't know who they were. I was just emailing support people and asking them questions, and they never responded as if they were some big shot. So, and again, this is pre-internet days, so I couldn't even Google and find who they were, right? So that was my exposure, understanding databases and EMR, again, all in Pakistan. I did my medicine training at my internship at NYU. And again, because of my exposure to mumps, when I was at the VA as one of my rotations, they were implementing the new CPRS EMR over there. And my first rotation at the VA was in the ICU. And my first weekend, I had 12 patients in the ICU to take care of, and I went home post-call at 5 p.m. on a weekend, and I made a decision that that's not happening again. I need to figure out how to optimize my process. So I wrote a template-based reporting application to expedite my progress notes. And immediately, next thing I know, my internship got converted into electives in IT. And I worked with the VA IT department at Heinz VA here in Chicago to build what is now the template-based progress note and CPRS. So again, very earlier on, got sucked into EMR. And again, because VA CPRS is also based on MOMS database, gave me a lot of advantage to understand how the database worked. I did my radiology residency at Geisinger, and same thing, as a first-year resident, I was asked to help find the PACS. So chaired the PACS selection committee at Geisinger as a first-year radiology resident, selected a beta PACS out of UPMC, built by Paul Chang, called Stentor. And we were the first site outside UPMC that implemented that PACS and did really well. And after that, they wanted to go to electronic health record. And again, the CIO asked me to be on the EMR selection committee. We ended up investing in a small startup out of Madison, Wisconsin, because nobody could satisfy our RFP. Remember, Geisinger was a HMO, so a lot focused on quality-based care, not fee-for-service models. And a lot of the RFP requirements or use cases were all quality initiatives that at that time, no EMR was addressing, because they were all built as billing systems. So the startup that we invested in at that time was called Epic. And the rest, you know how that happened, right? And again, Epic was also based on MOMS database, so it gave me a huge advantage, really understanding how the system is integrated, and a lot of work with the engineering team to make that work. I then decided, by this time, I was doing, my focus was on cardiac MR as my main clinical specialty. Again, I was focusing mostly on pediatric cardiac MR at that time, and I thought that's what I'm going to do as my clinical career. But then I think my wife convinced me, like there are only 7 people in the world who care about your cardiac MR research. But this IT committee meeting you go to and everybody sings your song, so why are you resisting career in that? Because as you see from a journey, right, I never thought in informatics as my career in the early days. So I finally gave in, and I thought that there needs to be some kind of training program in informatics. I also had what we call now the imposter syndrome, that didn't think I've gone through, undergrad education or college education on computer science, so I probably don't know anything. So convinced the chair at University of Maryland to start the first imaging informatics training program. And he said, I'll start it if you come and run it. So instead of doing a fellowship, I ended up starting a fellowship at University of Maryland in combination with the Baltimore VA. The claim to fame in Baltimore VA is that was the world's first filmless hospital. That when it opened the doors in 1992, it did not have a film library. So a lot of the early PACS implementation, all as Maryland, nation's first imaging in the country.
Junaid, we may have lost connection with our speaker.
Is he breaking up for you?
Yeah, I don't see him, Dr. Siddiqui, anymore in the group.
I was actually checking my own Wi-Fi. It seems like
There have been a reset.
Sorry.
Not sure what
So
happened.
we were actually at the VA Geisinger, Maryland, and when you created your fellowship, and right after that, sort of we lost you. So if you don't mind getting there.
Sure, I'll go back there. I have no idea what happened.
Maybe a Wi-Fi restart.
So anyway, so, ended up, as I said, can create country's first informatics training program. A lot of tech transfer happened out of that. A lot of startups came out of it. One of them that I led was initially called Yada Look. It was a natural language processing based startup that then renamed as Montage and then sold to Nuance Communication. I then got recruited by Hopkins to build the Center for Biomedical Imaging Informatics and Center for Technology Innovation, as well as the software tech transfer office at Johns Hopkins. So I did that with more than 40 million in annual tech transfer that happened at Hopkins. And at this time, we did some very interesting work in AI, and I got recruited then by Microsoft to come and start the medical imaging efforts as well as the machine learning AI efforts in 2007-8 timeframe. And I'll come back and show what we did at Microsoft. I left Microsoft in 2012 to start my next company called Higi. It's a medical kiosk that you see in grocery stores and pharmacies in North America. Scaled that company to about 11,000 of these devices deployed in retail pharmacies and health systems with over 70 million patients on the PHR, and exited that in 2018. Then a bunch of my former colleagues from Microsoft decided to start a data AI company. So I'm chairman of that company and got on a bunch of boards and started doing some investing. And then in 2019, I got approached by Dr. Jonathan Rothberg, who was starting this crazy idea of getting an MRI scanner to the patient's bedside, and joined Hyperfine as the chief medical officer and chief strategy officer to help get the device through regulatory process and commercialize it. So as you can see, I've done a lot of different things. So what I'll do is I'll walk you through just one aspect of it, how things evolve, right? So I've always had this thought process that, GPS has changed how we look at data, right? Just imagine if you had Excel spreadsheets every morning with road traffic data, with each street and the speed, and you had to figure out what route to take to work. You would have no idea. You would not be able to do this. But guess what? In healthcare, what do we do in healthcare? That's what we do, right? We get spreadsheets of data with lab values and medications, all the stuff, and now we have to compute in our head what is happening in the patient. And we have this vision that if you can represent the data in a more of a GPS manner on a human body, aka medical images, you can probably have a better understanding of and correlation, understanding of what is happening in the body. So we started this work on machine learning in 2003 to automatically classify CT scans based on anatomic regions, so you can represent data based on that. I won't go into details. It's the whole story how this even happened and started, because GPUs to do machine learning didn't exist in this time. So we were creating our custom proprietary FPGA cards to do this work. And that led to a lot of different works, right? Automated classification of images and anatomic regions, automated hanging protocols, and processing based on, now that you know what organ is in the image, you can change window levels automatically. You can create 3D post-processing applications to run automatically. You can create hanging protocols that happen automatically based on what you're looking at. And then we went even further, like, can we classify disease directly? So this was work to classify a meniscal injury and on knee MRs with high probability. As you can see, here's just one of the prototypes that we had done using machine learning to classify images and be able to represent that in an appropriate manner. So these are early deep perceptron networks. This is before neural networks were the hype, right? This was all based on SVM, regression forests, and deep perceptron networks. Those are the early versions of networks that existed at that time. So when I got into Microsoft, one of the projects we had was to how do you create photorealistic 3D imaging, right? This is used to be how images look like, right? And if you talk about 2008 timeframe, 3D data looked like that, looked nice. We thought it was great, but it didn't represent how, if you open the patient up, during surgery, how do the organs look like? And taking advantage of the Xbox team and some of the Microsoft research folks that were working on photorealistic, scenes in movies and in games, like how do we take advantage of all this amazing 3D stuff that is happening and bring into healthcare? And how do we do it in a manner that is very high performing, does not require, gigantic, workstation to do this? How do you do it through the web? And that led to creating the GPU-based volume rendering. And we really had to start from scratch. So Toby Sharp on my team rewrote the codec, the codec that is used to program GPUs. So NVIDIA had just come out with a Tesla card, and he, just to get the rendering to work really, really, really fast, rewrote the whole thing, what is called assembly language, basically is ones and zeros. And so this is now a prototype from 2009, what, 12 years ago. And just look at the frame rate on how, oh, if I can play it. And this is, I'm showing this sitting in Washington, DC, if it plays, where data set is sitting in Cambridge, UK. So this thing is doing 30 frames per second, 3D, 60 frames per second across the ocean, across the Atlantic Ocean in real time, right? So this is all running in a browser on my computer, whereas the data set and the cloud, the infrastructure GPU is sitting in UK. And that was the whole idea. How do you do photorealistic 3D? By learning how to reprogram a GPU, we decided like, hey, how do we now expedite our machine learning? Can we take advantage of GPU to do that stuff? So this is what the conclusion was, the 3D ray casting based 3D photorealistic 3D that we did. We ended up actually this became part of Xbox's arsenal. And I think Siemens licensed a lot of the technology from Microsoft for their photorealistic 3D. What do they call? Cinematic 3D is what they call it. So it was all the work that was done at Microsoft to improve medical imaging around that. So we then applied the same techniques to expedite machine learning on GPU. So this is one of the early versions of automated recognizing atomic structures on CT scans at 200 frames per second. So basically, as the scan is getting done, you're automatically classifying which organs were just scanned. And so you could stop the scanning in real time if you've already covered the body part, or you can automatically generate reports based on what you're looking at. So there were a lot of interesting ideas on how to do this. Again, the vision of how do you create a GPS for the human body. And this led to a lot of different things. And again, the big thing was that this is not image segmentation. We were trying to do image recognition to where things are. So in 2009, I got a call from another team in Microsoft that was trying to do the same thing, recognize something, but not in medicine, but in healthcare. And they said, well, we have this problem that we're trying to recognize where the head is, where the hand is. Can you help us figure out how to do this? And so the image on the right is actually the 26 body part segments that I did as a prototype from this grayscale stuff that they were showing me. And like at that time, I didn't know what the use case was. They just wanted us to figure out how to do this segmentation. So this was Jamie Shitton, Antonio Cremonesi on my team at that time, working with us, Toby Sharp. All of these were on the team at Microsoft working on this. And I'm sure you can guess what this is. This ended up becoming the foundation technology to recognize humans during gameplay. So you can see direct work that we were doing in CT scans in medicine and how we use GPUs to do recognition ended up getting translated to Xbox. Before this, they were trying to do a CPU-based work to do this, and they were running into problems, and we ended up expediting a lot of the stuff. And even a lot of people in my team at Microsoft in healthcare didn't know that this was happening because of such a hush-hush stealth project, and some of us were getting sucked into to support this also. And one of the key thing was we needed a lot of data to train, so that we didn't want the thing to work out of the required training to play a game. And so we had to create synthetic data. So the images on the top are real humans that we've segmented, and the images in the bottom are all synthetic data. And you can see some of these patients, the people have like elephantitis type legs and weird shapes, right? So, but what we realized was that if you had enough data, it overcomes all the errors in recognition, right? So we ended up generating 500,000 1-hour videos at 24 frames per second. The 24 times 60 seconds times 60 minutes times 500,000, and trained the model on that massive data set. And we had to build the whole architecture of 100,000 GPUs just to train this model to recognize human body parts. And that infrastructure ended up becoming the foundation of Azure machine learning that exists now at Microsoft. So a lot of these early things we were doing, trying to solve these problems, ended up becoming a crucial part of various aspects of Microsoft's technology. And this is the actual work that was published around this on using synthetics to train. And then actually at Hyperfine, we're using the same techniques now to train on stroke applications for the models that we are building. So again, a lot of this work is translating, you learn from one aspect, go to the next one, innovate over there, learn from there, go to the next one. And that's kind of have been my journey. And what made the whole thing worth is this is one of the early prototypes I brought home for teams to my kids to, see what it is. And they're playing a game and all they're doing is popping bubbles. This game never got launched. But
we're the jumpity boy. We're a jumpity boy. Jumping.
This is 2009, right? So, I mean, when you do this, when you see this, then all the work you've done, that's your reward and nothing else, right? So that was the exciting part of it. Anyway, I'm going to stop there on the journey, my journey there, and open up for question, and then we can go back to talk about Hyperfine.
My God, that was just superb. That's fantastic. I mean, a lot to unpack here from a wisdom perspective. I mean, entrepreneurship is a journey. I mean, people say, you had the idea on a napkin. No, it's an evolving thing. You have to stick to it. You need grit for it. Your wife knows you better than you know yourself. And then data is the new oil, and you have to be good at data no matter what your field are, and especially in medicine. And as you can see, the applications could be multi-tangential, and it can be applied from one industry to another, and you can innovate your way in or out of different things. And then it's amazing to see the history of CPU to GPU and actually coding at an assembly level, because that's really, really hard if anyone has tried to do that. I mean, now we live in a different world, right? I can go into Google Cloud and then get a TPU for 10 cents a minute or something, which is very different in your time. So, I mean, fantastic. I mean, and those who have been following the history can really appreciate like how hard that work has been. And the last point that you bring is very, very important, that we do all this for able to make sure that we can share this with our loved ones. So thanks for doing that. I really appreciate it. There are not much questions. I think we can just go directly into the key innovation. I think you have.
Junaid, let me ask a couple of questions, if you would.
Sure.
And I think we are a small enough group that we can allow people to unmute and ask their question. We raise your hand if there are a few people who are asking questions, if you want to be queued in, and feel free to start your video and jump in. So Dr. Khan, one of the things that often when we see someone who has so well achieved, it looks so hard to understand, okay, where did the process started? Because we're at the starting point at zero, and just copying someone who's already across so many finish lines is just so mind-boggling. In listening to you, it seems like that early exposure to programming, and then either getting opportunities or having interest and keep utilizing it in your med school, in your residencies, became that foundation which gradually got you to the point where you were doing such huge and tremendous projects. So any lessons from that, any suggestions on how to kindle that fire, how to get started, how to lay those foundations? And from was it your personal interest, was it the opportunities, did you have to go and ask for things, or you have to were you planning to design it that way, or it just happened fortuitously? Or any comments on that?
Yeah, I think you gave me a lot of credit, right? So once I started to build the habits of how to be a good leader, how to reflect, how to understand, right? I mean, I'll tell you, like in my Maryland days, I was egocentric, probably prick if you would ask some people, right? I mean, it would give people a hard time, was always on edge, things not happening, your classic, academic professor who's all the time at the edge and scolding people, and people are not, everybody's incompetent. That's kind of how I used to be. And I think what I've done, I think what has happened over time is really understood the value of leadership and how it's different from management, and the ability to reflect back and see what has contributed. I actively suppressed all of the things that I knew from a computer science point of view till I started doing informatics, right? So if you look at my early CVs or early residency applications, things like that, I would just not talk about this stuff because I thought IT, there's people who fix mouse and keyboards, right? That's kind of in my mental picture was, and did not think that was the, respectable profession or things like that. The very naive way of thinking. And I think in hindsight, it's those early experiences what has made me or enabled me to do things that I've been able to do afterwards. And again, I'll give you an example. And we have a professor at Aga Khan, Dr. H.R. Ahmed. Some people from Aga Khan would know who he is. 2 weeks into my first year of med school, he wanted me to work on some hypertension study he was doing just because he needed some data, somebody who could handle data. And suddenly here's I am somebody who can actually do this. And I hated that project, right? I had to go to obstetric clinics after my basic science work and classes I do in the evening and go measure blood pressure real time on pregnant women in Pakistan and do orthostatic hypertension, right? The stand up, lie down, and document that stuff. And I would be in the clinic, but clinic in Aachen used to run like till 8, 7 p.m. or whatever it was. So here's 2 weeks in first year med school student. I have to do my basic science, anatomy, physiology, biochemistry, all the stuff. But after classes, I have to be in the clinic, do this cut work on measuring blood pressure for the first semester. And it was affecting my scores, right? I was failing in my basic science test. But now then look at it, when I started Higi, I had such a deep understanding of hypertension and how it's measured and how the fluctuations happen, how somebody sits, somebody stands, that I would not be able to do what I did innovate in Higi if I had not done that project in 1990 because Dr. H.R. Ahmed made me do it, right? So something that I actively, despise doing. There's another one. One of the cardiologists in Aachen, Dr. Najib, wanted to do ACLS, real-time data collection, and cardiac arrest was happening. So I was carrying a pager 24/7, and any code that would happen in Aachen, I had to go show up and collect data, what drugs were given at what time, what happened, so you could be 2 a.m, could be in the middle of a class, middle of a lab, and you're running around as a single person doing all this stuff. It literally felt like internship in my 4th year of med school. And it was insane amount of, pressure. And again, the survival rate of the study was 2%. And I myself documented 150 patients. You can imagine seeing death after death after death. It created, psychologically, mental, emotional things too. But it really helped me understand how do you think about intensive care, how to think about patient in those critical scenarios, how to think about data access and need for emergent things. And it is so relevant to Hyperfine right now, right? Because I used to be in those ICUs every single day in those critical patients who we were doing things blindly because we didn't have imaging access, and just given the insight to it. So learning is that any experience that you do, even you hate it, whatever it was, you have no idea how it's going to actually go and impact the future. And I think the things that I did not like to do or actively suppress ended up becoming the main things that led me to do innovative things in the future. So, and that's, I think one thing I've also learned is that always be in a learning mode. So, probably you've heard a lot of successful people read a lot. I mean, in the pandemic, I read 130 books. In 2020, right? So I think that's my record of in a year number of books I've read. And again, I read both fiction and nonfiction type of stuff too, and it just be in a constantly learning mode. And again, I do a lot more on audio now than actual reading the books. But I think that's what has happened, building the attitude of, I don't know, I'll look it up. So not be afraid of trying new things, even if you don't know anything about it. Always be learning, and there's no individual and there's no idea that is wrong. I'll tell you, the Higi was supposed to be a data platform, was not supposed to be a kiosk company. And we were struggling to figure out how we're going to collect this data from patients to understand risk in the population. So again, we can provide solution. It was an intern on the team that said, what about these kiosks? And my answer was, those are stupid, never work, always incorrect. And he goes, exactly, right? So why won't we go disrupt and build something that is better, right? And And that's pivoted. It was not my idea at all. It was an intern, and I couldn't convince him to stay with me. I mean, he's doing big shot now. He's a big shot strategy person at Humana, running the whole Humana strategy, but he was an intern in my team at that time in 2012 who came up with the idea that we should be doing kiosk. And so again, the Toby Sharp that I talked about, the example, Toby was a developer, and like this whole story on how he even got to GPU, we all resisted. We did not want him to do this. And we did a fun sprint in which he decided in that fun sprint, that's the thing he's going to work on. And it completely changed the whole history and enabled all the things that you saw. So again, sorry, Danish, such a long answer to your question, but it's not that simple answer.
Yeah. No, that's wonderful. I have one more question, but I see that Professor Sarwat had raised his hand. I'll let him introduce himself and ask his question, and I'll cue myself a second after him. Professor Sarwat, please go ahead.
Ji, Assalamu alaikum. Dr. Khan, how are you?
I'm good, how are you?
Just a matter of history. I used to know Dr. Bob Grenis at Harvard Medical School when I was there in 1983. And we all used to think that, we don't know what he is doing. And we never understood what he's up to. It was boring, and really nobody really listened to him. No, my question actually is that, first of all, your presentation and your career has been exceptionally inspiring. And obviously, all of us want our children and grandchildren to follow your course. And looking back, you could say what choices you made, but obviously, if you look prospectively, there must have been several roads to take from every juncture that you took. And there obviously tremendous amount of uncertainty at the time, when you embarked onto something. Now, the question is that what are some of the things that might lead to your kind of career starting from now looking forwards in terms of technology, since that's your field, and how to embark on them, how to choose them?
Wow. Dr. Sarwat, you always have very deep questions. Like sometimes I wish I have all these answers, right? For me, a lot of things have happened because there's the time, the place, and I am, and the opportunities come up, and I've jumped on it, and sometimes I've not jumped on it, and regretted later on not to do the stuff. I really wanted to do cardiac MR as my clinical specialty. I had really big ideas and ambitions of what I wanted to do. And I even got into fellowship at UCSF with Charlie Higgins to do my cardiac MR fellowship over there. But then life hits, right? We found out that my wife's pregnant and we are going to have our first child. And she was going to be in her 4th year radiology residency at Geisinger in Danville, Pennsylvania, where I'll be sitting in San Francisco in the warm, sunny California, enjoying my fellowship. That just would not have worked. So I called Charlie asking him, like, what options do I have? And he said, listen, we would love to get you next year. So why don't you come and we'll figure out how to get Pfizer fellowship too. So, but suddenly now I'm in my 4th year radiology residency. Every fellowship is already taken. I have to look for a new fellowship. That became the driver. Like I had to find something now. Nothing existed in the 3-hour radius that I could drive to and while support her during her first pregnancy. And then it was my program director's secretary who said, like, all these informatics things you're doing, isn't there a training program there you can look for? And he's like, there's nothing. He's like, maybe they just don't advertise. And that led me to start calling every single department, asking. I literally would have department chair, I'd do the list of all the state of computer application radiologies, board members, American Association of Medical Informatics board members, committee members. I had found all their phone numbers, would call and ask anybody who has informatics fellowship. And it's like, what is that? Was the normal question. Like, is there such thing as informatics training program? Like, not in imaging. So there were PhD programs in informatics that Bob Grenis had and a few other people had, but nobody had a fellowship. And I didn't want to go do a 4-year PhD somewhere else. And again, my radius was from Geisinger. So it was max I would go to is Pittsburgh. It was Baltimore. It was Philadelphia, Hershey, that was the radius I had to look something in and convince. So, and then I had to convince people to start a fellowship program. Can you imagine a Pakistani kid in Geisinger calling chairmen of radiologies, trying to convince them to start informatics fellowship? I mean, this whole story if you, on YouTube on Elliot Siegel and me talking about how that happened. Random call, somebody call and say like, hey, you need to start informatics fellowship and I'll come and run it. So, I mean, he took a chance, right? The dean at University of Maryland, and he took a chance on that, but I'm sure I did something right to convince them to do this. And you just have to be hungry what you want, right? And just go after it. And that's, I mean, I give my wife's example, right? When I was doing my internship at NYU, she had just finished her med school and she had a year before her internship would start, and she wanted to find research positions. And she basically found every single assistant professor, associate professor in the island of Manhattan and would physically show up with her CV, knock on doors and say, I want to do a research with you. Ended up doing it with Vivian Lee, who ended up becoming Chief Science Officer at NYU, then Dean of University of Utah, and now he's head of Verily, the Google's healthcare program. So when Vivian meets, she never introduces me as Siddiqui radiologist. She says, oh, he's my former mentee's husband. She's the only person who introduces me like that. And any of the big, I mean, obviously, she's now in the same circle that I am in informatics, technology, entrepreneurship. But that's my wife's connection, right? In which she did her MR 1 year of research with Vivian Lee, who had just finished her fellowship at NYU, had just become a faculty and was looking for somebody to help her with her research. So again, you have to be tenacious. You have to go after what you want. And just, you will get 100 no's, and then the 100, if you haven't tried 100 times, I remember Pfizer did 110, physical visits with all the faculty on the island of Manhattan to try to get a fellowship program. And I probably made similar amount of calls. And I mean, even now when I raise money, when we raised 90 million at Hyperfine, right? I mean, I'm probably talked to over 100 VCs before we were able to raise 90 million to do that stuff, right? So it's never easy. No matter how many times you've done this, it's always hard, and you just have to have that passion behind it, and just don't take no for an answer, and just figure out how to do it and learn from it. If it's not working, then you have to learn, fail fast, right? Can't keep doing the same thing again and again and again, expect something to change. I hope, sorry about that, gave kind of a long-winded answer. It's all about tenacity. It's all about going after what you want. And it's all about, learning from your mistakes and changing fast.
That's so wonderful. That's amazing. And thanks for sharing all of this. It's really inspiring and very, very useful information that is often not discussed or taught, when we are being even mentored. One question that I wanted to bring up to you, Dr. Khan, was there seems to be just this aversion to industrial side in the clinical side, especially academics. If you're working, the academics don't want you to interact, don't want you to, you will somehow catch a virus and get corrupted, and you will be useless for the academic sides, and they don't want you to have coffee with anyone or lunch or go attend a meeting or talk anything. So there develops this kind of a resistance, and there's a thought, often we still joke, oh, he has gone to the black side. So if someone took a job at an entrepreneur, at a company, they say, oh, he has gone to the dark side, he's gone to the black side. Well, how do you see that? How do you make your transition? What can we do to reduce those barriers or change that culture, especially on the academic side of medicine?
Danish, I was the same way. It took Microsoft 6 months to convince me to move, right? So I would have the same exact attitude. And funny thing is, like, I did more academic publications at Microsoft than I did before Microsoft. Like, I think in 2010 or 11, I did 22 peer review publications at Microsoft, right? So, and we were doing so much in machine learning and so much in medical imaging stuff, right? There was just so much happening. I mean, even at Hyperfine, I don't even remember how many, like we had 12 abstracts at ISMRM from our team. Right, so it doesn't mean that you're going to end, your academics or passions that you are going. Just be clear why you are joining somebody and why you're doing something, right? And what is your goal? What is your vision? And how you are constantly learning and improving things and keeping your academic mindset. I mean, we are still academic mindset, even in Hyperfine. I mean, there's so many PhDs in the team, and they're all academic. They're all postdocs. They've all done their thesis. They've all published. They've all been, I mean, we have the editors from Radiology Journal is on the team as a clinical scientist. You know, we have people who are moderating sessions at conferences, you know, teaching people as part of our engineering team, right? So to me, it's a part of the same continuum, right? So I think that it's always like, you know, everybody you talk to non-physicians, they think every doctor is the same, right? I mean, how many times like, oh, yeah, something going on in here, you know, you're a doctor, you know how to do this stuff. I was like, no, right? So it's the same thing on the computer science side of things, engineering side of things. We think they're all the same. You just need a coder to do software, and they're way more specialized than anything else, right? Somebody who can do websites and build amazing applications would have no idea how to build an app for iPhone. I would actually build a pretty bad thing because it doesn't translate. You know, at least in medicine, we learn all these things, you know, and have basic understanding. In engineering, they specialize so early, so fast that it's almost like, you know, medicine and dentistry, right? You don't know anything about the other specialty. So I think it's just why you're doing it and why you want to do something and how you're going to make the difference. And my eyes opened up, right? I also had the same perception that, oh, this industry is going to be all, you know, just business people and things like that. And it is very different. It's very fast moving. You know, you react fast, you innovate fast, you move fast. I mean, Hyperfine, in December 31st, we were 47 employees. This Monday, we'll be 108. Right? So, you know, the team's growing really, really fast. So.
Wonderful. Professor Sarwat, do you have a comment?
In fact, I have a question. My question to Dr. Khan is how can you help IT and artificial intelligence in Pakistan?
Oh, absolutely. That's a great aspect, you know, thought process there. I think all this starts, to be honest with you, everything starts with the—
Yeah, sorry, can I interrupt you? Let me just ask you a question. If we, the Apna merit group or Apna people, get together, let's 10 of us get together and raise $1 million to start a startup IT company in Pakistan, what are the prospects and how can you help them?
Okay, so I will do completely opposite. I would start with the problem first. I would find what is the problem you're going to solve first, and then figure out how to solve it, right? And AI may not be the right answer for it, right? So I've always done that. You know, I've always—
I have a lot of problems in mind.
Yeah, so I think the right thing to do is get the team, identify what problem you're going to solve. Is it going to create a big impact or not? Is it, if you do solve it, will it actually be the issue with building a business is that it has to be viable financially, right? It has to have a business model. It has to have the right product market fit. So I think the early work is really supposed to be, make sure you understand the problem, make sure it's a big problem, make sure people care about the problem, and then don't get married to an idea, and then iterate to figure out how to solve it the right way in the right context for the right audience, right? And sometimes it will be a mobile app, sometimes it will be, you know, nothing to do with technology, right? It'll be, maybe it requires humans to do it. But I think that's how I approach a lot of these issues. I always recommend think about the problem first, think about what it is, and then build the right team that go and figures out how to solve it. And they should have all the tools available to them on how to solve it. If it requires machine learning, AI, data, absolutely, then they can go solve that stuff. But don't start with what in it, otherwise it becomes like, you know, you've identified a hammer and now you're looking for nails. Where can I use the hammer? It just becomes more of a idea looking for a problem solution then.
Awesome. Thank you so much, Dr. Sarwat, Dr. Bhatti, for all those questions. Just to summarize, entrepreneurship is a mindset. Be humble, open to opportunities, work hard, make sure that whenever these things come by, you pay attention enough. Look for the pain point, as you suggested in your last point, and the solution that is marketable, profitable, and financially viable. So Thank you again very much. I really appreciate all that. I'm very grateful for this advice, especially for young physicians. So I'm going to give you the mic back, Dr. Khan, and then you can discuss about Hyperfine and its applications in neuroradiology and what's on your roadmap specifically for neuroradiology. As a neuro ICU physician, I'm extremely excited because the portable CAT scanner changed the way I practice medicine, and that was a big deal. And I'm looking forward for your MRI machines to show up on different places.
Yeah, absolutely, right. I think the vision for Hyperfine really started with Dr. Jonathan Rothberg, who invented the next generation sequencing and really made his money in that. And then also in 2011 started Butterfly Networks, which is the point of care ultrasound. And Jonathan approaches the problems more from, somebody in his life, somebody he loves has a problem, and he kind of fixates on it and tries to solve that, and takes advantage of, what I call vertical integration, and taking advantage of things that have happened in the industry outside of healthcare, and how do you bring those learnings into another domain. So that led to, in 2014, this idea that, there's limited access to high quality care. There's so many people who are living in chronic diseases that can benefit from better way to look at the disease through imaging, through sensing, whatever you want to call it. And then just, 2/3 of the world just doesn't have access to imaging, being able to monitor continuously and do intervene. And all these things are large, expensive, require expensive installations, requires experts to use it, and a lot of training, and then are only available in specialized centers. And then that is kind of what the vision was. And the conclusion came to in that initial discussion in 2014, 2015 was that how do we come up with a non-radiating high advanced imaging solution to the patient's bedside. So if you look at MR 1.0, these were permanent magnets, low field, started in the late 70s and the 80s. And then in 1986, Picker, which became GE, eventually commissioned the first superconducting magnet, 1.5 Tesla. And then all the research in the ultra low field completely stopped, and people start focusing on high field to get imaging. So these machines got bigger, require special rooms, special HVAC units, and a lot of the other issues that are with advanced imaging. And then people kind of completely forgot about low frequent field strength MR for a long time. I think almost like 2015, where the interest in that again started. And then so what we call now MR 3.0 is bringing that MR capability with advantages of 40 million increase in compute power, 20 million increase in microelectronics and material science, and signal processing, and all that stuff that has happened over 3 decades or 4 decades, and bring that into to the patient's bedside. So we've released our first portable MRI scanners, FDA cleared, in clinical use today. We just keep deploying. If you're following us on social media, you can see, pretty much weekly, we are deploying new devices everywhere for clinical use. And then we had to really think through from scratch, right? I mean, we had to really think through how to think about a device that can be affordable, that can be portable. So the first thing we had to figure out is, how do we address the requirement for Faraday cage for an MR scanner? Like, how do you remove that? And the reason for Faraday cage is because there's so much RF and electromagnetic radio frequency noise in the environment. And that's what you're trying to shield for, so you can detect the subtle signal that comes from the hydrogen atoms in the body, like in water molecules, basically, in your body. And so we invented noise canceling technology. The way your headphones have noise canceling, we have noise canceling technology that cancels out all the environmental noise. So the monitor in the room, the respirator, the ventilator in the room, all the other gadgets and metal does not cause any interference. And MR is very sensitive to temperature. So we had to figure out, how do we measure ambient temperature and correct for that as we are doing imaging. The second biggest problem we had to solve is, how do you build a magnet, right? So typically, because MR is a low volume device, people make magnets by hand, and it takes 6 months to make one magnet. And if you import them or you manufacture them somewhere else, the transport cost to secure the magnet and all the safety that goes with it just becomes really, really hard. So we decided, like, okay, fine, what if we didn't import the magnet, and we actually create an assembly robot that assembled it on the assembly line. So we're not importing raw magnets. So this is what you're seeing right now. So the blocks are the raw ore converted into blocks that get shipped, so in a box, right? So they aren't magnets, they're just metal. So no need to do any kind of safety transport of this stuff. And then the thing that is hanging from the ceiling here, this is the two robotic arms here. This one magnetizes, and this one is the big one that essentially cures the magnet on a plate for the magnet that builds. So we reduce the manufacturing time from 6 months to 6 hours. And that's how we can reduce the cost, 20 times reduction in cost of manufacturing magnet, and then speed in manufacturing also. So we not only did we invent the technology to do the scanner, but also the technology to build the whole machining and the tooling and manufacturing process. We had to reinvent that. I mean, that's how Tesla has evolved, right? It's not just building electric car, it's also the manufacturing of electric car is also what's led to it. And what it enables is scenarios like this, where you can bring the MRI to the patient anywhere, no issues with electronics, IV pumps in the rooms. The image on the left is the North Shore University Hospital. Is the first COVID deployment we did in April of last year. This is a neuro ICU. Patient was a COVID positive patient, had altered mental status changes, and they couldn't figure out what to do with it. And when this scan was done, there were 110 patients on ventilators, and they didn't have a transport ventilator to take a patient down to radiology, and plus risk of COVID and all the other stuff. So this was being used over there. The image in the middle is in the ER at Yale. I mean, look at all the room electronics and metal in the room. That physician with the iPad is controlling the scanner. It talks wirelessly to the scanner. That's where the console is. Console is an iPad. And by redoing the magnet, using a permanent magnet, and redesigning the gradient coils, we've reduced the power requirement to something similar to a coffee maker or a blender, right? You can literally plug it into any wall outlet you want. And we also had to rethink how the user interface works, right? So we had to make it really simple, because this could be used by radiology techs and MR techs. It could be used by a community worker in sub-Saharan Africa and community center, right? So we had to think through, how would somebody do it? So it's a single button scanning. The scanner figures out where the patient's head is. You just hit play and does all the 3D sequencing on its own. You don't have to go plan the sequence. It does all auto alignment. It has motion detection capabilities, so to generate diagnostic quality images every single time. And because it's wirelessly connected, data goes immediately to a physician's phone so they can interact with it. We also do what is called progressive rendering. So as scan is happening, as case space is getting filled in, we're generating images. So even though the scan time can be 5 minutes to 10 minutes, but you are seeing images within minute, 2 minutes of scan starting. And then we have AI application through the cloud to help with assist in diagnosis, as well as viewing capability through a browser-based PACS. And obviously we connect to local hospital PACS also. Our first clearances for neuro applications, so we do T1, T2, FLAIR, and DWI with ADC map. We also have our AI application cleared through FDA that does volumetrics, so volumetrics of the ventricles, the brain, midline shift, and things like that automatically. And we are working on a lot more things in the future. We are active trials going on for other body parts. So for C-spine, for extremities, upper and lower extremities. We have trials going on contrast agents. So dedicated contrast agents for our device is not cleared through FDA yet, but we're looking at different contrast agents, including ferumoxytol, spion agents, and higher laxivity gadolinium for those applications. And we are also trials going on for intervention. Because of our low field strength, we don't have those issues that you see with metal going inside MR environment, right? Here you can see the needle very clearly going through a lesion in this phantom example here. And just imagine opening up image-guided procedures on the patient's bedside. Right? You can have a scanner right at the bedside and be able to do procedures with image guidance right at the bedside. I mean, we see Hyperfine as an ecosystem, not just a device. We'll keep building new devices for intraoperative use, emergency use, screening applications. We'll keep supporting them with AI applications to better image quality, reduce imaging time, image guidance, even disease detection. And then we'll have consumables such as contrast agents and procedure kits to be able to do image guidance intervention in the long term. So we think of ourselves as solving the entire ecosystem of care continuum, from monitoring to sensing to diagnosis to therapy, and MR is just our first forte in the vision of where we are. I don't know if you have time to go through some clinical cases, or should I stop?
If you have time, sir, feel free to go ahead.
Right. So
We will record it, put it up for all the people to consume later.
Sure. So so I'm going to start the story in Blantyre, Malawi. It's one of the sites that has one of our scanners. And this is Dr. Terry Taylor, who runs the Blantyre Malaria Project. They had a GE MR scanner that broke down 2 years ago, and they just couldn't get parts or anything to repair it. And they were really desperate for getting more scanners. So this is an Mercy James Institute, where they're running this cerebral malaria program. And our scanner was delivered to them on March 11th. And here's her tweet that they scanned the first patient 4 hours after they uncrated it. Nobody from Hyperfine went with the scanner. So we trained them all remotely, and then Dr. Taylor's team uncrated it and we're scanning patient and saving lives 4 hours after the crate arriving. I mean, this is unheard of, even in the US, to be able to do imaging this fast for an MR scanner. So here's a story of 13-year-old Malawian boy who presented to hospital with acute, profound, decrease in consciousness. Obviously, this is a malaria clinic, right? So they were concerned about cerebral malaria. And here are what the images are. I'm not sure if Dr. Sarvat wants to comment or somebody wants to comment what this is. Again, 13-year-old boy with hyperintensities, mostly in the posterior portion of the brain. So this is non-cerebral malaria, right? This is Press syndrome. And Press syndrome is a benign entity. It's good if promptly treated, and all you have to do is reduce the blood pressure. And they immediately recognized it, treated his blood pressure, and patient recovered, right? So here's a classic example of a place where there's just no access to imaging, and without doing MR, you would have no idea what is going on with the brain, right? There's just no way. CT would have been normal, everything else would have been normal, labs would have been normal, and if it is not treated, you would have had pretty bad outcome. Here's another one, scenario male presented to MGH. This is now a US scenario, right? In the emergency department with acute change in mental status. Initial workup was done with non-contrast CT. Patient was transferred to the ICU. There was some hemorrhage detected on CT, and I'll show the images. The EVD was placed for supportive care because they thought nothing can be done for this patient. And then while this patient was being stabilized to figure out what else going on, why the bleeding started, they decided to do a SOUP scanner, one of our scans. So here was the initial interparenchymal hemorrhage, interventricular hemorrhage. You can see some midline shift. Diagnosis hydrocephalus with interparenchymal and interventricular hemorrhage. But here's our scan, right? So as you can see, there's some high signal on flare on the right side, but very classic wedge-shaped, high-intensity diffusion rate imaging, hypointensity on flare, and this would demonstrated, focal territorial infarct. It was not recognized by neurology staff over there. And this was, raised diagnosis of superimposed vasospasm due to the hemorrhage, and the patient had balloon angioplasty to open up the vessel and recover the stroke, right? So this was not a candidate for TPA, right? And this did not really require mechanical thrombectomy. This was more of a vasospasm due to hemorrhage causing an infarct. Again, providing immediate direct results for this patient and changing care. Here's an example of another Malawian boy with obstructive hydrocephalus because of ependymoma internally. I think I'm going to stop here. Looks like there are a lot of questions.
Boy, this is extremely fascinating. And we'll, just to remind everyone, the innovation doesn't come just because of the actual portable MRI. There's a whole manufacturing process that got innovated, a whole user experience that was defined, a whole new use case scenario that was redefined. And by the way, if you follow Hyperfine on social media, the way they're actually selling the device is actually amazing as well. That's a total disruption of the industry as well. So go ahead and make sure you follow on Twitter and LinkedIn. And then the way they're actually making it available is just fantastic. So just to make that additional point, and then we'll get to the questions in a minute. If you don't mind, if being the moderator, I can ask the first one. So as you can see that, one of the biggest advantages is that you can actually keep it in a room without any magnetic interference. And the second one is you can potentially even, do some needle-based or even metal-based while you're getting the MRIs done. One of the key things is that when you are actually doing this, is the image quality up to par? And if so, how did you achieve it?
Yeah, that's a great question. I'm going to be a little bit selfish here, and I'm also going to bring in one of my other team members. So Dr. Eddie Knob, who's a senior medical director on our team. Eddie was the director of neuroradiology at NYU for 20 years. So he is the expert in neuroradiology and pretty much taught most people doing neuroradiology in the country, right? So I wanted Eddie to talk about how he made the switch from academia to clinical practice to Hyperfine too. But I think the thing that we've done is, as I said, right? I mean, there has been so much improvement in electronic signal processing techniques that is not applied to permanent magnets or low field imaging at all, right? So we basically did that. If you look at images done at 1.5 Tesla in the 90s and look at 1.5 Tesla images now, field strength is the same. But look at the image quality, how it has changed, right? So we basically brought in better sensing capability, better signal processing capability into the place. And now in the future, we are adding more machine learning and deep learning capabilities. That's my expertise into plane to even improve image quality. Again, we are not doing at the image level. We are doing all this stuff at the signal level, at the when we are getting the data from the patient's body, right? We're doing it at that level so that it's less of the image-based artifact getting introduced. It's more processing. Eddie, you want to comment on image quality?
So my view as a clinical diagnostic neuroradiologist is that this is not a replacement for 1.5 or 3T, but as Khan has indicated, it can give you answers to specific clinical questions in situations where you may not be able to get that answer, or it's just too difficult and dangerous for the patient to get them. So with knowing the question you want to answer, you're going to get that answer. Do you need the resolution of a 3T to see a large territorial infarct? Do you need the resolution of a 3T when it's 3 in the morning, you're in the ICU, the patient's a post-op, and all of a sudden there's a significant change in mental status? Did he bleed? Is there significant mass effect? Did his vents blow up? Does he have an extraaxial collection? We can answer all of those questions without putting the patient at risk and getting that answer in a phenomenally timely fashion, because you don't have to transfer them down. That's how you have to think of this system. That's how I think of the system.
Beautifully put, sir. Including in the neuro ICU, you cannot tell me like how many times I have to go through root cause analysis just so that the patient had to go to a CAT scan and the EVD came out. Right. It's just the use case scenario that you defined is extremely important. And the example that Dr. Khan just suggested, that the DWI flare mismatch, how you can actually go ahead if it was a balloon angioplasty or intraarterial TPA because it cannot seep, you can actually get to a lot of limb and life, right? I mean, it's literally directly limb and life as far as the stroke is concerned. So that's great. Absolutely. There were a few questions about cost and availability in Pakistan. And then I'm grateful that you have been answering that in the chat as well. Thank you very much. Danish, do you want to have some questions, sir?
No, I mean, I don't have, but I can definitely see all those use case scenarios popping in my mind as a neurologist when I'm on call, and all the challenges of a patient, especially in ICU and neurocritical care setting. But I think the advantages are beyond just use in US, and some of those examples were so beautifully shown by Dr. Siddiqui. This will revolutionize the imaging across the world and not just change things in North America. Thank you.
I'll give you an example. Unfortunately, the scan wasn't used for this. So I get a text message from Dr. Aisha Kamal from Aachen. So they have a scanner there for pediatric infant asphyxia and neonatal brain development sitting in pediatrics. So she's texting me 7 in the morning, Pakistan time. So patient has arrived in the ER in the middle of the night, 65-year-old with new onset tremor. And ER admitted it. Even though neurology wanted MR done first to figure out what's going on, all the labs are normal, but the patient's cardiovascular status is getting worse. Altered mental status is happening, weird neurological symptoms, and they have no idea what is happening. Now the patient's unstable. They can't take him to the MR or CT scan, and they're totally blind, right? So the option is dual LP to see if there's encephalitis happening here because symptoms are so weird. is a tumor, you'll find tumor cells. And her thing was like, can you convince PEDS to let me use the scan in the ICU in AKU? I was like, yeah, why are you calling me? But anyway, just give you an example that how much enthusiasm even in AKU has, and which people are fighting about, where the scanner should be. And it's just tremendous amount of use cases that come in, once you start to realize that you can actually do this.
Yes, I mean, the use cases would be amazing. And then understanding, again, what Dr. Knopp said is to make sure that you have the question in mind. And it's extremely important in a value-based healthcare model that we actually have to start asking the question before even ordering the imaging and then deciding on the tool. I'm going to give the mic to Dr. Tipu Siddiqui. He has a question. Sir, if you don't mind unmuting yourself.
So this is wonderful. I overslept, so I didn't see the first part, but I was really looking forward to, and Dr. Siddiqui needs to be congratulated, obviously, and he is, I should say, miles ahead of what we know. But I had a question that is more for the AI, and Junaid, you are very interested in that too, but is that can we look at tissue, can we look at autopsy samples and use microscopes to apply AI to using, I don't know what paradigms are being used or what algorithms to try to bring up the signal that would actually lead us to a better understanding at a molecular level or at a level that would tell us more about the pathogenesis, not the obvious stuff that we see on pathology, but in terms of using various kind of immunostains to see what is the real commonality, not just the morphology.
Yeah, I think, I had a project in Microsoft, we used to based on unsupervised learning, right? So the idea was there are other features. So let me track back here, right? So for AI algorithms to be successful, it's all about the data it's trained on, right? Because you don't actually sit and write an algorithm, right? You basically tell the machine, like, here's data. This data has this thing positive, and this data is normal. Now you go figure out what's the difference, right? So literally no human sits and programs this stuff. You basically feed data to known algorithms that then figure out what the differences are and then build the model by themselves. That's why it's called AI, because humans not creating those algorithms, machines creating the algorithms based on data that was fed to it. So the things you're talking about, right? So a lot of work that is happening right now in AI is all about based on what humans can see. So what happens is the way imaging-based AI happens is a human goes and labels the data set or traces where the pathology is, and we tell the machine, like, hey, this is lung cancer, this is breast cancer, this is this, this is that, and these are normal, these don't have the pathology, and now go learn what the difference is. The true things you're talking about requires what I call unsupervised learning, in which humans can't see it, but we know this patient had this thing, but we don't know what were the features, or features not visible to us on imaging, pathology, what are you going to call it, and then tell the machine, like, can you figure out, are there any features at the image level, at the signal level that can actually detect the difference between this and the normal data set versus that we have not been able to see ourselves, right? But to do that, you need 10, 20 times more data. So just to give you an idea, for unsupervised learning model, for one feature, we require 1,048 data sets, right? And if you're looking for something that has 100 features, there's 1,048 times 100 is the data sets you need, right? So like if I'm looking at particular disease and disease prevalence is 1 in 100,000 patients, you pretty much have to have data from thousands and thousands of institutions across the world to be able to even build that model. So I think the biggest bottleneck in the scenarios you're talking about, everybody wants to do this, that's the vision of this, is the lack of availability of data to do that kind of detection using AI model. I mean, as I said, right, in Xbox, we ended up generating 500,000 data sets to train those models to be able to work how Xbox Kinect worked out of the box. And I mean, I'm bringing some of those techniques into Hyperfine to do this stuff, but we'll see how we are successful or not. We don't have the answer yet, but I think that's the promise of AI, and I see AI as a lever for us, right, as a physicians. It's something that we use to instead of seeing one patient at a time, improving one patient in a day, you can now touch 1,000 patients and improve 1,000 people's life at the same time. And that's what AI brings in and enables us to scale really fast.
Could you
words of wisdom. So
sample
sorry,
1,000?
go ahead.
Sorry.
Could you sample? I mean, obviously, the limitation you pointed out in terms of access to numbers, but let's say within each individual, one can get an improvement of signal if one sample not one specimen but neighboring specimens. Let's say in the motor cortex or some other place, you have 10 samples from each patient or from each person or from each mouse, and then you do let's say for the sake of argument, 500 of them, you have already increased it to 10-fold or more. Does that help, or is it not useful?
It's magnitude more than that's needed to train. So for it to be generalizable across patients, you have to have multiple patients. I'll tell you what, we used to run into problems when we didn't. So when in our early data sets that we trained, the thing that I showed in my data size on detecting human anatomy, we had data from GE scanners, Siemens scanners, Philips scanners, but for whatever reason, we didn't have Toshiba scanners. So our accuracy was 96% on those scanners. But as soon as data came from Toshiba, our actually dropped to 30%. As a human, I couldn't see a difference between the CT scan done on Toshiba versus Philips or GE, but our algorithm would completely fail because whatever it was learning, the feature was learning, it was drastically different for the machine and just would not work. I mean, even the same thing we've seen in clinical, right? MGH did dense breast cancer detection. Their accuracy was 92% in dense breast. And then when they apply the same algorithm on data from Brigham, the accuracy dropped to 12%, right? So there's a whole idea of generalizability that requires multiple patients, multiple instrumentation, so that the algorithms that are built by the AI can actually work across patient population, across practice scenarios. There's so much variability in MR. I mean, the reason you don't see a lot of MR-based AI detection application because a lot of vendors have IP on how they do sequences. So the T2 sequence is the most common, most stable across all vendors. Flare, diffusion, all these gradient echo images, they're all slightly different, right? And that's why pretty much all AI applications that are designed on MR are done on T2 weighted images, because that's the most similar looking sequence across vendors. And problem becomes really, really hard because no two vendors have the same flare looking image, between themselves, just because how they have done their IP around it. So I think those are great ideas, Deepu. I think, I'm sure definitely somebody's looking through those scenarios, but and as I said, nothing's ever, all these thought process and ideas, what creates out of the box thinking around this, right? So, I would encourage, if anybody's here want to try it out to see if that model can work the way you're talking about, why not? We'll find out even if it works or doesn't work, right? We'll get some kind of answer.
I mean, we would love to try that out because we have at least some of the reagents. Sure. And both at the molecular level as well as at the pathology level. But, we would need obviously your help, or Junaid or somebody, to make it somewhat at least testable.
Sure.
No, I mean, those are excellent points, Dr. Siddiqui and Dr. Khan Siddiqui. You need 5 big V's of data. I mean, variety, velocity, etc. And then on top of that, you have to have some standardization of data input, and then generalizability depends. I mean, clearly it's much easier when you have the Huntsville unit, right? No matter what the CAT scanner is. That's why we can see Rapid AI, Viz AI actually being implemented significantly, or EKG, because at that point in time, there's the electrodiagnostic data from EMG nerve conduction studies is pretty similar, because that's a waveform. The minute you actually have the variability of data in such a difference with 1.5 Tesla, 5 Tesla, different vendors, how the actual data is being extracted, it becomes harder and harder, and you require more and more and more data to actually communicate that. I mean, medical knowledge by itself doubles every 3 months, and we're seeing a logarithmic change because it's already at a exponential change to an algorithmic change. So this is exciting stuff to be in medicine. And then thanks to Dr. Siddiqui, we can see that, if you work through it, stay with it with passion, perseverance, you actually do make not only a difference in your personal financial life, but also at a greater scale to human life in general. If there are no more questions, I'm going to go ahead and ask our two EC members to quickly, unmute themselves, introduce, and then we'll then end up the meeting today. Adil, do you want to go first?
Sure. Dr. Kalia, thank you so much for this great presentation. So just a brief introduction. I graduated from Dow Medical College back in 2013. Did finish my neurology residency and then kind of got excited into learning signal processing and artificial intelligence. So I'm currently a neuroengineering PhD student, third year right now. And, start learning how to code at the age of 30 is difficult, but kind of, slowly finding a way, a solution to do that. So I will be reaching out to you, Dr. Siddiqui, for, troubleshooting on the ideas. And also when I apply for my KA23 award in the future as well. So thank you so much.
More than happy to help.
Is Taimur still on?
Assalamualaikum. Thank you, Dr. Junaid and Dr. Siddiq for your time. It was very valuable and I learned so many things. Thank you. Thank you. Thank you for everything, your time.
I'm very grateful to all the members that joined today on this webinar. This will be available on social media. Please make sure you post it and then say thanks to Dr. Siddiqui in public on Twitter and LinkedIn so that this word gets out. Make sure you go to Hyperfine website, make sure you download their brochures, make sure you actually forward them to your hospital administrators, make sure you send them to your CEOs, CMOs, and everyone so that if they are missing that information, they need to get it out there. So it's extremely important that we support, as Dr. Khan has graciously given his time, given his situation. So thank you again. Dr. Khan, any last words?
Well, I'm just humbled by you guys asking me to do this. When you're doing all this work, it doesn't feel like you're doing innovative stuff and something you're really in the weeds of it, trying to solve daily problems. And it's very flattering when you get asked to do this stuff. But as you said, it's we are a mission to make a difference in people's life and creating a social impact at the same time. So not only are we growing in the US, but also in Pakistan. So if there's anybody you guys know needs MR capability in Pakistan, please send them our way also.
Thanks again. Thank you, everyone. Have a nice day. Assalamu alaikum.